Right, so let us again start from where we left off in the previous video. So there we have already seen this exercise. Here in the plane, n number of lines are drawn in such a way that no two different lines are parallel to each other and no three different lines pass through a single point. So then we have to figure out into how many regions these lines are dividing the plane. And in fact, we saw the number in the previous video. Now, since this exercise is appearing in this chapter, we are supposed to solve this using induction. So we start by claiming that that number is the answer. We claim that the n lines divide the plane into n times n plus 1 divided by 2 plus 1 number of regions. So that means for induction we have to start by taking n equal to 1. When n is equal to 1, the required number of regions is 2, because if you have only one line, then that line divides the plane into two distinct regions. And what happens to this number when n is 1? 1 times 1 plus 1 divided by 2 plus 1. So this the first term becomes 1. So the number is 2. So these two things are matching. That means the claim is true when n is equal to 1. This is the basis of our induction. Now assume that n lines divide the plane into n times n plus 1 divided by 2 plus 1 regions where n is some positive integer. And you have to understand that this of course is our induction hypothesis, so we are assuming this, and you have to understand that this assumption is in the context of this exercise. Not any n number of lines will do this. For example, if all your n lines are parallel, then the number of regions that these lines generate, that is different, that is not this number, but these n lines mean n lines drawn with these conditions in mind. Okay, so because whatever we are writing is within the solution, so we are not again explicitly mentioning the conditions. Okay, now if we draw an extra line that is not parallel to any of the existing n lines and also does not pass through the points of intersection of any two of the existing n lines. Then what happens? This extra line, that means satisfies the conditions. It is not parallel to any of the existing lines, and it also does not pass through the points of intersection of any two of the existing lines. Keep in mind that the existing lines are already satisfying that condition, so three of the n existing lines don't pass through a single point, but two of them can. Okay, and they will, of course, because if you take any two of these n lines, then since those two lines are not parallel, they will cross each other at some point. So this new line will avoid those points. In that way we have drawn this new line. Then we get n plus 1 new regions besides the existing this many regions. Hence, the total number of regions after introducing the new line is n times n plus 1 divided by 2 plus 1 plus n plus 1, and if we add these two things together we get okay, let me just show the calculation. If we take n plus 1 divided by 2 common out from these two terms, then here we have n and here we will have 2. Which is just this number if you replace n with n plus 1. So this completes the induction. And proves our claim. And that completes the solution. But you may have noticed that there is a very big gap in this solution. How do we know that n plus 1 new regions are being generated by the introduction of that new line? For that, let us see some concrete cases first. and this solution, the way it stands now, is actually incomplete. For the sake of clarity, let's just do that here. How do we know that exactly n plus 1 new regions are being generated? That is the question now. So let us start with a single line. When you draw a single line, of course, the situation is so easy that it's almost trivial. There are exactly two regions. The line divides the plane into two regions, and you can understand that this line extends on either direction without any bound. Now the next stage is to keep in mind that we now have two regions. Then in the next step we are going to introduce one new line which will not be parallel to this. That means no matter how we draw this new line, these two will intersect somewhere. So let's make them intersect here itself, the part of our plane, that is the plane of the board that we can see. Now this new line, recall that these were the original regions before the introduction of this new line. Now this new line actually crosses through both the regions. Okay, it passes through both the regions, and thus dividing this region into two parts and also that region further into two parts, giving us four different regions now. 1, 2, 3, 4. And it has done that by dividing the existing regions into two parts. A given line, of course, when it passes through a region, it will cut the region into two halves. Well, I should not say halves because right now we are dealing with unbounded regions. You see, before the introduction of this line, we had this unbounded region and that unbounded region. So after introducing this line, we can in fact say that this new line has divided this unbounded region into two halves, because both the new regions, sub-regions if you want to say, they themselves are unbounded, so you can call them halves. However, if you introduce one more line, then a region will be generated which is not unbounded and which is a triangle. So we should not say half, but into two parts. Okay, so now our along the way, let's keep track of the number also. When we had one line, the number of regions was 2. 2 gives us 4. Okay. Now when we introduce in the next step one more line, what happens? That new line will not be parallel to either of these two. However, that new line at the same time will not pass through this point of intersection. So you can draw the new line in this manner, or you can draw it here. It does not actually matter. Do you see why that does not matter? Does not matter in the sense that whether you draw the line in this way, either on this side of this point of intersection or on that side, the number of regions, new regions it will generate will not depend on this choice. That is because if someone is looking at this board from that side, from behind this wall, then for them this choice is like another choice on this side. Okay, so it will not actually matter where you draw this line as far as this number of new regions is concerned. Okay. Now there is one thing to observe. Note that before the introduction of this new line, to emphasize the fact that this is a new line, let us make it a dashed line. Okay, so before the introduction of this dashed line, we had 1, 2, 3, 4 regions. Now this dashed line has passed through 3 of them. 1, 2, 3. But it has missed one region. And while passing through these 3 regions, it has divided each of these 3 regions into 2 parts. This has divided this region into these 2 parts. This region into this part and this part. This region into this part and that part. Okay. So the third line misses one region, but it affects 3 regions. The first line actually affected, for the first, actually we don't have to look at the first case. The second line, when you introduced the second line, it affected 2 regions. So alongside we write the number of affected regions. Introduction of the third line, okay, let us also see how many regions we now have. 1, 2, 3, 4, 5, 6, 7. Here the number of affected regions is 3. Okay. Let us draw one more line. So this now becomes our regular line, one of these lines. And now one more line. We can also draw that one more line in any manner we want. It will not affect the number of newly generated regions. Let us extend these things a little bit so that what we are getting will become clear. So this is our new line now. Okay. This new line clearly you can see is not parallel to any of these 4 lines, and also this new line has avoided these points of intersection. Okay. Now how many regions are getting affected? This region has got affected because it passes through this 1. This one has got affected. Keep in mind, now we have this line also. This region has got affected. 2. This one has got affected. 3. This one is also being affected. 4. But the number of regions which are not affected are these 1, 2, 3. So here the number of affected regions is 4. So you can see that this number matches with this number, the number of affected regions. Okay. And what is the actual number here now? Affected as well as unaffected. Since the affected regions are each one of them is getting divided into 2 parts, so 4 affected regions give us 8 regions. Okay. and the remaining 3 gives us 11. Let's see also whether our formula is working. This is our total number of regions. For 1 we have already seen. For 2, this, if you put n equal to 2 here, this 2 and that 2 will cancel out. 2 plus 1 is 3, 3 plus 1 is 4. When you put n equal to 3, you will have a 4 here. 4 divided by 2 is 2. That 2 times 3 is 6. 6 plus 1 is 7. When you put n equal to 4 here, that 4 divided by 2 is 2. 2 times 4 plus 1 is 5. That means 10 plus 1, 11. Okay. So that means at the nth step, the number of affected regions will be n. Okay. Now, what have we written here? We get n plus 1 new regions. Where is this thing coming from? You see, you look at this step. Introduction of this line affected 4 regions. That means it has doubled the number of regions, and those extra regions are coming from these affected regions. So, besides these 4 regions which are already there, of course, the number 4 is already there, but the regions themselves had got affected. This was a single region previously. Now it has been divided into 2 parts. One of them is this and the other is this. So this new part corresponds to the original region plus 1 extra. Here also, this was our original region, which has now got divided into this and this bounded region. Say the bounded region corresponds to the original region, and this is plus 1 extra. Here also in this region, we have got 2 parts. This part, say this bounded part, this triangular part corresponds to the original region plus 1 extra. So we are getting 4 extra regions here. At the nth step, we will get n extra regions. Now this is the n plus 1 step because we already had n lines when we introduced 1 extra. So that's how we get n plus 1 new regions. But in spite of this explanation is actually not a justification for this, because this is something general, and that is why I was saying that this solution is incomplete. Is there no way of making it complete? Of course there will be some way of making this complete. Means rigorous, a mathematical statement where there is no gap, no very large gap like this. I mean, these are only just some observations. No, what you can do is you can try to prove this itself, that at the nth step, when you introduce the nth line, the number of affected regions is n, and hence they will generate n new regions. So you have to add n to the original number of regions before the introduction of that nth line. And for all these things, you can visit this web page. Here you will find that there are proofs which do not involve induction. They involve recursive relation, and in one proof I think it involves some geometric trickery. So what is the URL? Cut the knot. These are not underscores, okay, these are dash. dot org/proofs/lines divide without any gap, and it's case sensitive, so capital L means capital L, plain dot html. Okay, you visit this web page and there you will see many things. We will try to complete it, or you can also try. I could have just easily copied one of those solutions here. However, those are not induction proofs. The next one, exercise 2.25, show that for all integers n greater than or equal to 2, there are two parts to this exercise. In part 1 we have to prove this: 1 plus a whole to the power n is greater than or equal to 1 plus na for all positive real numbers a and the second part asks us to show this: the nth root of n is strictly less than 2 minus 1 over n. I am noticing that although this text, this algebra book by Gregory is quite elementary, I mean it's for the beginners, but the exercises are extremely interesting and some of them are quite, I mean they force you to think. Nice exercises. Here we won't use induction, we will use the binomial theorem because that's very easy to use. If you want, you can use induction also. By the binomial theorem, one plus a whole to the power n is 1 plus n choose 1 a plus n choose 2 a square, etc. Okay, should I proceed like this? I can write like this, however there is a slightly better way of doing this calculation. This is also equal to a plus 1, and that is n choose 0 a to the power n. Oh, but then okay, let's just do it the way it's going, no need to overthink it. n minus 1 a plus n choose n. Now we isolate this and write the rest of the terms separately, and we know that this value is nothing but n. So na plus, for the others, since we don't need the others actually, we won't bother to write them except this one perhaps. So we write these two things and write the rest of them together. So we don't bother to simplify these other terms. A to the power n minus 2 plus it is given that n is greater than or equal to 2. Okay. Now note that a is a positive real number, and from the definitions of these binomial coefficients we know that they are also positive. In fact, each one of them is a positive integer. So the thing that you see here within square brackets, this thing itself is a positive real number. That means this entire thing is greater than or equal to 1 plus n a. So that's how you just achieve this inequality. You cannot have this inequality if a is not positive. Okay, now so that is part 1, and now for part 2 what we do, for part 2 should we use part 1, and I think that way it will be easier. Let us see. Using part 1 we have, so we need to prove that this is less than 2 minus 1 over n, which is equivalent to proving that n is less than 2 minus 1 over n whole to the power n. Two minus 1 over n whole to the power n can be written as 1 plus 1 minus 1 over n to the power n, which is 1 plus n minus 1 divided by n whole to the power n. Now we are able to use part 1 and write this greater than or equal to 1 plus n times n minus 1 divided by n, because we can take n minus 1 divided by n in place of a, and that is because n is greater than or equal to 2. So n minus 1 is greater than or equal to 1, and in particular n minus 1 is positive, n is also positive, so this quotient is a positive real number. So this becomes what? 1 plus n minus 1, that is equal to n. That is, Now if you take nth root on both sides, which you can do because the numbers involved are all positive. Oh, but there is one do we have greater than or equal to or strict inequality here? I think I have made a mistake in taking this down. We will have strict inequality here. Equality occurs in only one case, where n is equal to 1, because in that case the left hand side is 1 plus a whole to the power 1, which is 1 plus a, and the right hand side is also 1 plus a. If n is greater than 1, then we have strict inequality. Oh, and we have strict inequality. You see, this thing within this square bracket, this is a positive real number, not a non-negative real number. There is no question of having this term inside the bracket equal to 0. It is positive. So we do have strict inequality here, and that is why here also our application of part 1 gives us strict inequality. So here we get strict inequality. So that's just it. Next, exercise 6. Show that the binomial coefficient 2n choose n is less than 4 to the power n minus 1 for all positive integers n greater than or equal to 5. Okay, so this is less than, not also equal. This is less than this only for these values of n, where the least is 5. Now for this we will use induction. Note that when we put n equal to 5, here the binomial coefficient is 10 choose 5, which is equal to 10 times 9 times 8, 7, 6, 1, 2, 3, 4, 5 divided by 5 factorial. And 5 factorial is also 5 times 4 times 3 times 2 times 1, which is it's unnecessary. I mean, you don't have to write 1. So 3 and 2 get cancelled out with 6. This is 2. This is 2. So that means $252, which is less than when if we put n equal to 5, that means 4 to the power 4, 16 square, 256. Yes. So that means the claim is true for n equal to 5. Assume that 2n choose n is less than 4 to the power n minus 1 for some integer n greater than or equal to 5. Then we now concentrate on this binomial coefficient, which is equal to 2n plus 2 choose n plus 1. This, if you apply the definition, is 2n plus 2 factorial divided by n plus 1 factorial times 2n plus 2 minus n plus 1 factorial, which is also n plus 1 factorial. We can now simplify things by writing the numerator as 2n plus 2 times 2n plus 1 times n factorial. In the denominator also we can write n plus 1 times n factorial and all again n plus 1 times n factorial. Oh, what? Okay, what the hell? This is not correct. This is not n factorial, this is 2n factorial. Here we have n factorial. So you can see how quickly I can make mistake. Right, let us now there is however one cancellation. You can cancel n plus 1 and here you will get 1 n plus 1. Cancelling those two terms you get 2 in the numerator. So this will be, after that cancellation, 2 times 2n plus 1 divided by we will have 1 n plus 1 times. Now in the numerator we originally had 2n factorial. Now in the denominator we have 2n factorials, which we can write like this. So that means 2 times 2n plus 1 divided by n plus 1 times 2n choose n. Now we can apply our induction hypothesis. This is less than 4 to the power n, that means this product is less than 2 times 2n plus 1 divided by n plus 1 times 4 to the power n minus 1. Okay. Now what? We want this thing to be less than or equal to at least 4 to the power n. Is that true? You can just simply write this step just like this. It's a fact that this is less than or equal to 4 to the power n, and that's why we can write 4 to the power n. But let us also see why that is true. This is true if and only if 2n plus 1, let's keep 2 for the time being, is less than 4. You can cancel 4 to the power n minus 1 from both sides. And if and only if, this is true if and only if 2n plus 1 divided by n plus 1 is less than 2, which in turn is true if and only if 2n plus 1 is less than 2 times n plus 1, which is nothing but 2n plus 2. Because this inequality, we can clearly see it's true, so that's why this is also true, because we don't have just implications, we have double implications, so we can go back. So that means this is true, and 4 to the power n is nothing but 4 to the power n plus 1 minus 1. Hence, by induction or by the principle of mathematical induction, our inequality is true. And there the solution ends. Then exercise 7. We define the Fibonacci sequence via this formula. Fibonacci sequence, the nth term of the Fibonacci sequence is denoted Fn, f suffix n. So the first two terms are both equal to 1, and if n is an integer greater than 2, then Fn is defined to be the sum of the previous two terms in the sequence. Show that for every positive integer n, if n is less than or equal to 7 divided by 4 whole to the power n minus 1. For this also we will use induction. Note that if 1 is 1 and when n is 1, this is also equal to 1. So that means this is the basis of our induction. But let's see another step, because otherwise we won't be able to use this formula. Also, if 2 is 1 and and 1 is less than 7 divided by 4. So you see that this equality is possible only when n is 1. For higher values of n, we have strict inequalities. We will now see. Now, assume that our required inequality is true. For some integer n greater than or equal to 2, then if n plus 1, by definition, because n is greater than or equal to 2, so n plus 1 is strictly greater than 2, that means we can apply this formula here. So this is equal to fn plus fn minus 1. And because of our induction hypothesis, here we need to assume the stronger hypothesis. For the ordinary induction will not work here. For all integers, there is in fact we can start it from 1 where n greater than or equal to 2 is some integer. So for m equal to n and m equal to n minus 1, we can apply these formulas, these inequalities. So the first term is less than or equal to 7 divided by 4 to the power n minus 1, and the second one is less than or equal to 7 divided by 4 to the power n minus 2. We can take 7 by 4 to the power n minus 2 common out. That will leave us with this. (11 divided by 4), and 11 divided by 4 turns out to be less than 7 divided by 4 whole square. Let us see how. So if you multiply both sides by 16, then we will get 4 times 11, 44. 44 is less than 49, so you can go back, and this is to the power n, which is minus 1. So by the principle of strong induction, Fn is less than or equal to 7 divided by 4 to the power n minus 1 for all positive integers n, and that completes the solution. Then exercise 8 with Fn as in the preceding exercise, that means the nth term of the Fibonacci sequence. Show that for any integer n, Fn is actually equal to an expression like this: 1 plus square root of 5 divided by 2 whole to the power n minus 1 minus square root of 5 divided by 2 whole to the power n divided by square root of 5. You may know that this number 1 plus square root of 5 divided by 2 is known as the golden ratio. If things are made with this ratio in mind, for example, if you draw a rectangle such that the ratio of its length to its breadth equals this number, then in some sense the rectangle looks quite aesthetically pleasing. It looks like how a rectangle should be, not too long so that the rectangle is almost like a strip of paper, also not too narrow, also not square. It's more rectangle like. Golden ratio appears in many places in nature. You probably already know these things, and it appears in many places in mathematics also. Anyway, so here again we are going to apply induction. Note that F1 is 1, and what about this? In order to write this ratio somewhat more manageably, we write 1 over root 5 in the front. To the power 1, do we have n here or n minus 1? We will see. Okay, I think we have n here. This is equal to, let me just simply write 1 and then let us see how it is equal to 1. 1 plus root 5 minus 1 minus root 5. That means 1 over 2 minus 1 over 2, they will become 0. Square root of 5 divided by 2 minus minus plus square root of 5 divided by 2 is square root of 5. That divided by square root of 5 is 1. Okay, so when n is 1, this formula is true, and that is the basis for our induction. Assume that for some integer n greater than or equal to 1, if n is what is being claimed, then if n plus 1, we should not start with fn plus 1. We should start with this expression itself, where in place of n we have n plus 1. Or we can in fact start with fn plus 1 itself, because otherwise how are we going to get fn plus 1? But for that to happen, I should have checked another value, that is n equal to 2. Also, like before, if 2 is 1, and okay, this time we need to do a little bit of calculation. We can use the a square minus b square formula. Here we won't have the irrational part, and 1 over 2 plus 1 over 2 is 1. That means this term is just 1. And what about this one? Root 5 divided by 2 plus root 5 divided by 2. That means this, which is equal to 1. Okay, now we can make our assumption. that is the induction hypothesis. Assume that for all integers, and here also we have to apply strong induction, for all integers m lying between 1 and n, we have f. Okay, in the previous solution, did I write the condition for the induction hypothesis in terms of n? I think I have done that, no? But while assuming, we started by considering m. So in this solution, I think I have made that mistake. You have to assume this instead. And then this actually is not a single inequality, it is a number of inequalities, as m varies from 1 to n. So here also, and now I am remembering that. So you please rectify that part. Here also we will have to write the expression or our assumption for m, if m is this. Okay, now we are ready to carry out the induction step. Then, and this time we will start with fn plus 1, so that we can write fn plus fn minus 1. Now fn, according to our induction hypothesis, is 1 over root 5 times this, minus 1 minus root 5 divided by 2 whole to the power n, plus 1 over root 5, 1 plus root 5 divided by 2 whole to the power n minus 1, minus 1 over root 5 divided by 2 whole to the power n minus 1. So 1 over square root of 5 can be taken common out, and okay, let's just show all the steps instead of saying them verbally. We will, however, write the terms in a somewhat not straight forward way. What I mean by that is, after taking 1 over root 5 common out, we are not writing this plus this, but instead we are writing these two terms together because they are similar, and we are going to again take terms common out. That's why, like that, minus 1 minus root 5 divided by 2 to the power n minus 1 minus root 5 divided by 2 to the power n minus 1. Okay. Now this can be taken outside, n minus 1. minus 1 minus root 5 divided by 2 to the power n minus 1 times 1 minus root 5 divided by 2 plus 1. Keep in mind we have taken minus of this common out. So inside we have both the terms plus, not positive numbers, because this is not positive, not 2 point something. Yes, so this first term is negative, but positive terms means we are not writing minus here with these things. That's what I mean. Okay. Now, what about this? This becomes 3 plus root 5 divided by 2 minus, and this like that becomes 3 minus root 5 divided by 2. And here we can do a little trick. We can multiply and divide by 2. It will become apparent why we do that. Minus here also we multiply and divide by 2. Now if you look carefully, this thing is actually 1 plus root 5 whole square. In the denominator we are getting 2 square. In the numerator, if you expand this, what will you get? 1 plus 5 plus 2 root 5. 1 plus 5 is 6. 6 plus 2 root 5. Just like that. This one is 1 minus square root of 5 divided by 2 whole square. Note that expanding the numerator, we will get minus 2 root 5, but we will get 1 square plus root 5 square. So here also we are getting 6. The minus term is with this one. So we are now almost there. N minus 1 plus 2 is n plus 1. So you can see that we have got that formula with n replaced by n plus 1. Hence, by the principle of strong induction, we have for every positive integer in this. And this completes the solution. Next, exercise 9. This exercise is about chocolate. A bar of chocolate is a rectangular array consisting of r rows and c columns of unit square chocolate pieces. With thin lines. Okay, this is comical, no? I mean, this is why people hate mathematics. If you have a bar of chocolate, uh, will you really think of these things? It has, say, 5 rows, 4 columns with some lines or seams in between so that you can break the chocolate pieces, that too unit square chocolate pieces. Some people hate mathematics because of these things, that it takes the romance out of everything, apparently. Anyway, lines separating rows and columns. Okay, a single action, so they are defining an action, consists of taking one bar and breaking it along a line. Breaking it along a line separating 2 rows or 2 columns. Or reducing to smaller bars. Right? show that it will take precisely r times c minus 1 number of such actions to turn the bar into RC square pieces. Of course, when we get such a bar, the only action we can think of is to eat it. We think of these type of things only when we have to share, reluctantly of course. This can be done using strong induction. Or with no induction at all. What I will do that no induction. We will take that no induction approach. However, I urge you to use induction and prove this. To apply induction, what you have to do, you have to keep one of these two things constant. Say you keep the number of columns constant and you apply induction on the number of rows. So here the situation is like this. And in fact, I won't write a formal solution, I will just show you the idea. So this is such a bar, which of course is not how an actual chocolate bar comes. You can consider it as a part of the bar which has already undergone some breaking. So what the author is saying that we are going to call these things actions. Either you break this bar along this line, creating two smaller bars along a row line or along a line between these two rows, or you do that breaking along a line between two columns. Whatever you do, after performing the action once, the original bar will be divided into two smaller bars. So here you can see that the number of rows is 2 and the number of columns is 4. So how many actions do we have to perform? This says that the number will be 2 times 4 minus 1, that is 7. And you can see how you can do that by first of all breaking the bar along the horizontal lines, that is lines between the rows, between two consecutive rows. If you break this bar along this line, then you will get these two bars. And then to break them further, in order to have only those unit square pieces of chocolates, separate all of them, you have to then break these two bars again along these lines parallel to the columns. So how many breaks will you need? 1, 2, 3. Here also 1, 2, 3. So the number of horizontal breaks is 1 less than the number of rows. 2 rows are there, so that means in between them there is one line. So 2 minus 1 breaks. First of all gives us these 2 bars, and then here you need 3 breaks, here also you need 3 breaks. So the number of breaks along the lines parallel to the columns is the number of columns minus 1, that is 3. But how many such 3 breaks? 2, and that is equal to the number of rows, that is 4 minus 1 times 2. If you do this in general, you will get this figure, this numerical figure. If you want, you can perform these actions in other possibly different manners, but this I think is quite straightforward. So we have R rows and C columns. So first, if we perform the horizontal breaks, then the number of breaks is the row number minus 1, plus then we perform the vertical breaks. Now after performing these R minus 1 breaks, we have rows of chocolate chips, chocolate pieces. So the how many vertical breaks? The number of columns minus 1. And how many such C minus 1 operations or actions? The number of rows times. And this is equal to RC minus 1. Okay, so you need to perform that many actions in order to break this into RC number of unit square chocolate pieces. And finally, we have exercise 10. Show that for every positive integer n, there exists the positive integer k. And integers ai belonging to the set consisting of 0 and 1, such that n is equal to a naught plus 2a1 plus 2 square, or they are writing it like this. Usually these AIs are written before writing the powers of 2, but anyway, 2 cube a3 etc. plus the final one is 2 to the power k a k. If you look at this exercise, you can quickly recognize that this is nothing but the binary representation of the integer n, positive integer. To keep things simple, we are taking positive integers. So again we apply induction. When n is equal to 1, we have k equal to 0 and a not equal to 1, because of this equation. Assume that for some positive integer n, there exists a positive integer k and integers ai coming from this set, okay. Now we have to prove that n plus 1 is also expressible in this form. So this is our induction hypothesis. This much is basis. Then n plus 1 is equal to okay. Now if a naught is 0, then we are done. Why? Because then n plus 1 is an expression which is like this: 1 plus 2a1 plus 2a square, 2 square a2 plus 2 cube a3 and so on, where 1 can be taken as our new a naught. That is because 1 is coming from this set. However, we will run into a problem if a naught is itself 1, because then we will have 1 plus 1 equal to 2. Okay, so let us write the steps, which I think can be somewhat made more streamlined by doing something here, but let's just go with the flow. If a naught is equal to 0, then n plus 1 is 1 plus 2a1 plus 2 square a2 plus 2 cube a3, etc. plus 2 to the power k ak. Okay, so this is again one such expression because this number is 1, so it can be taken as our new a0. If a0 is equal to 1, a0 can either be 0 or 1. These are the only two possibilities. Then what happens to n plus 1? N plus 1 then is equal to 2 plus, because now a0 is 1, so 2 plus 2a1, and that 2 plus 2a1 can be written as 2 times 1 plus a1 plus 2 square a2 plus 2 cube a3, etc. Now whatever we did with a0, and actually if you see closely with 1 plus a0, we can now do with a1. So let's just write those next steps. If a1 is equal to 0, then n plus 1 is again of this form. Then n plus 1 is 2 times 1 plus 2 square a2 plus 2 cube a3, etc. plus 2 to the power k ak. And note that here in place of a0 you can write 0. 0 can be our new a0, okay, and our new a1 is 1. If however a1 is equal to 1, then okay, now what happens to n plus 1? N plus 1 now becomes, if a1 is 1, then 2 times 2 is 2 square, then this becomes, and that 2 square plus this 2 square a2 gives us 2 square times 1 plus a2 plus 2 cube a3 . Okay, so that means in each of these steps, I mean it's a sequence of cases, right? If a0 is 0, then our job is done. If a0 is 1, then our job is not done. Keep that in mind. Then n plus 1 has been expressed in this form, but this form is not necessarily the form that we want. It depends on what a1 is. If now a1 is 0, then again our job is done. But if a1 is 1, then again we have n plus 1 in this form, about which we don't know because this now depends on a2. And you can see that this process will go on, but there is an end to it. The process goes on as long as the AIs keep becoming 1. Then the process moves to the next stage. The moment you have an AI that becomes 0, the process stops. Continuing like this, if a0, a1, a2, etc., all of these things up to say ak minus 1 are equal to 1, then the process goes on. Then n plus 1 becomes what? All of them are 1. So 1 plus 2 plus 2 square plus 2 cube etc. plus 2 to the power k minus 1 plus 2 to the power k ak. We don't yet know what ak is, but this becomes what? We can apply the formula for the sum of this geometric series. So this will become 1 times 2 to the power number of terms plus 1. Is it k plus 1? K minus 1 k plus 1 minus 1 divided by 2 minus 1, or am I getting it wrong? Let me just see. I don't exactly remember the formula for the sum of the terms of a GP, but no problem, we can quickly figure out the formula from this small calculation. Okay, so if we do this, s plus 2 to the power k, then we get what? Or okay, not s plus 2, this is not ap, this is a gp, so we multiply by the common ratio. That gives us 2 plus 2 square plus 2 cube etc. plus 2 to the power k minus 1 plus 2 to the power k. Now if we subtract this from this, then on the left hand side we get s, on the right hand side we get a number of things will get cancelled. 2 square, these things will get cancelled. We will be left with 2 to the power, okay, so this is 2 to the power k minus 1. So this is 2 to the power k minus 1, minus 1 is appearing here, plus 2 to the power k ak. Anyway, we will see what happens depending on what ak is. Now if ak is equal to 0, then n plus 1 is 2 to the power k minus 1, but how can we possibly take care of minus 1? Will that not create a problem? If we write this, how to adjust this minus 1? 2 to the power k minus 1, we want to be able to have an expression like this where the coefficients are either 0 or 1, each one of them, and the powers of 2 keep on increasing. We have minus 1. Minus 1 can be taken care of in what way? Can we write this as 2 to the power k? No, I don't seem to be able to see how one can handle this case. If on the other hand ak is 1, then what do we get? If ak is 1, we get 2 to the power k plus 2 to the power k, and then there also we have minus 1. So here, for right now it's not coming to me how this minus 1 will be handled. So that means we are slightly stuck here, but I'm going to end things here We will start from this, we will complete this in the next uh, video, next Saturday, and then we will see further things. So that will be all for today in this video. You can write in the comment section below. And tomorrow we have analysis, and day after tomorrow we have number theory. After that in our cycle, excuse me, graph theory will come. So that's just it. See you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.